In this lecture we will discuss Armax and Box-Jenkins models and how one could determine the model orders of such processes. Basically the case we're looking at is when you have external data that can somehow affect what you're observing. So for instance, say that you try to model the power consumption for the heating of a city, and you also know the temperature outside of the city. Obviously the temperature outside will affect how much power is being consumed, so when it is colder there will be more power being used up. Somehow you would like to use this information about the temperature when you create your model for the power consumption. So that can be done in many different ways, and often what we do is we will have a so-called Armax or a Box-Jenkins models. The difference between our previous models is that we will now add a component that is the input x of t here, which we allow to be delayed d. Say for instance that we are measuring the rainfall in some city upstream, and we would like to know how much water we will get to the city downstream. Obviously there will be a delay before the water raining upstreams will arrive at downstream. This delay we would like to allow for. This is the parameter d, so we would like to determine d. Then we also have the same a and the z's polynomials as we have used in the ARMA processes before. And of course we have the special case if these are either the a part is gone, then we have a max process, or if the c part is gone, we have an arcs process. But the thing to note here is that for an Armax process, we have the same a of z polynomial affecting both x and e, which is a very strong assumption, and we would like to relax that one. And this can be done using a so-called Box-Jenkins model. The Box-Jenkins models allow for a different a polynomial for the x and the a parts of the process. We still include the d here, and so what we'd like to do is we would like to determine the model order p for the ARMA part, that is the part described by the driving noise, and we would like to determine the r, that is the model order of the AR components for the external input. Furthermore, we would like to determine the q, the ARMA part of the noise process, the MA, as well as the S, which is the MA part of the modeling for the input. So in the following we will be looking at how to determine the models P, Q, D, R and S. Assuming here for the moment that if we knew those orders we could proceed to estimate the coefficients. And then we will look later on in the course on how we should go about estimating these unknown coefficients given that we know the model order. Okay, so to do so, we begin by ignoring the structure of the noise, just denoting this E tilde, and trying to determine the model orders of the B and the A2 polynomials. Dividing B and A2, we get the transfer function H. That is looking at the input of the filter, x of t, going through H, adding an additive noise, E tilde, and getting y of t. Now we wish to determine this filter H, and hoping that from H we can get the model orders of the B polynomial, that's the model order S, and the model order for the A2 polynomial, that is R. This filter, we can write a Z transform of it like this, and we assume this to be a stable, causal, and linear filter. The causality means, of course, then that the component hk for k less than 0, they are all 0. Okay, so if we begin by ignoring the noise completely, we just say that the E of t, E tilde part is gone completely. Then we can rewrite, by multiplying by A2, we can get this expression. So that means that if we knew h of z, we would be able to solve this equation and find the model orders for A2 and B, and as well as the delay, by just identifying the coefficients in the corresponding polynomials. If we look at that, we will see that if I multiply it out, the first thing that springs out is that the hk coefficient should be 0 for all k's less than d. That is, if I would look at the impulse response, I should see something that is 0 up to point d, and then there would be something which is then the impulse response. So that means I can use this to determine d by just looking at the impulse response. Furthermore, if you look at the other parts, you can see that they are a little more complicated. They are having a sort of a wiggling behavior depending if k is equal to d or larger, right? But then as k is greater than d plus s, we see we have something like an ARMA behavior here. But so the question is really, we know how to reach d, but how can we reach the r and the s? And in general, this is a quite difficult problem given that these equations are non-trivial to solve in those cases. But we will make the assumption that r is either 0, 1, or 2, because that covers most of the cases we're interested in. So let's look at the case when r is equal to 0. If r is equal to 0, that means that we have no a2 polynomial. There is nothing that divides it, and that means that the transfer function will contain a finite number of pulses. They will start at position d, and then it will have a finite length, and it will stop at d plus s. Meaning that I can look at the impulse response, and I can then conclude from the length of it what I should pick s to. So in the particular case of r is equal to 0, this is essentially an easy task. Now, when r is equal to 1, that means that we have one single pole in our system. We get an impulse response. We should get an expected impulse response that looks like an exponential decay that starts as position d plus s. So that means I can start looking at when the impulse response starts exhibiting this exponential decay behavior, and from there I can reach s. Finally, in the case when r is equal to 2, I have two complex poles typically, and I will then exhibit a damped exponential or ringing behavior in my impulse responses. So my envelope will be exponentially decaying, and I will see something that rings or just exponentially decays. And the decay will again start at d plus s. So basically I can look at the impulse responses in these three cases and try to determine what is a suitable order of d and s. So we have gathered all these results up here in this table. So this is the impulse response, and you can see here that if I have a d of 2, I will have 0, 1, 2, right? As the position where my impulse response should start. And if I have an r is equal to 1, that means that I will have this as position 0, and I have one component. Same here with 0, 1, 2. So I can determine the length of the impulse response, and that will give me s in the case when r is equal to 0. For the case of r is equal to 1, then I will have this exponential decay, as I mentioned, and it will see, as you see here, it will start at d plus s. Depending on if s is 1, 2, or so forth. Same thing with the exponential decay. You can see I will have this ringing behavior, and it will start at position d plus s. So this is 0, 1, and that is d, and d plus s is this value. That is where it will start. So how do we know the impulse response? Let's look at that. So I will write out the impulse response like that. And then in the case that I'm looking at, I will assume that the means of the different processes, x and y, are 0. I can easily subtract the means here so that this will be true. And I will make the assumption that x of t is uncorrelated with e. That is, that my noise has nothing to do with my input. If I then compute the cross correlation, you will see that the cross correlation will contain the filter coefficient here for the different lags. That if I normalize, I can reach, the cross correlation will reach the coefficient for the impulse response. However, it's rather complicated because I have this later order lags kicking in that causes problems for me. But however, in the particular case, when the input is a white process, this nicely simplifies so that I actually can see the impulse response directly from the cross correlation. So that means that I can, for a white input, estimate the impulse response directly by estimating the cross correlation function. Now, so let's look at an example here when we have an input. This is an AR1, so here x of t is our input. This is a real valued system, and I would like to determine the model order for it. So if I rewrite the process as a transfer function and do the polynomial division, you see I will get an infinite sequence here of a1, a1 squared, and so forth. So if I rewrite the cross correlation, I will get an exponential decaying component. For the ACF, you see I have exactly the same. It starts at 0, and then there is an exponential decay that kicks in. So I should get an exponential decay looking like this. This will then tell me in this example that I have no delay, so d is 0, and since the exponential decay is there, I should have r is equal to 1. However, the input is typically not white. So in the case of rain, obviously it's not going to rain like a white process. It will have some structure, and this is going to be true for most things, that they are not white. If so, we cannot directly estimate h of k because of this very complicated structure linking the impulse response to the cross correlation. But we can be smart. We can create a white input. So to do that, we will model the input as an ARMA process like this, and then we will rewrite the input as being driven by a white noise. So notice that in this new Box-Jenkins formulations, the input is a white process. The transfer function is a little bit more complicated, but the input is white, meaning that I should be able to look at the cross correlation between W and Y and there be able to reach the impulse response. However, I can be smarter than that. If I multiply both sides by A3 divided by C3 and form a new process epsilon like this, what will happen is that the C3 and A3 components here will cancel. So I will now get the transfer function I am seeking directly from the cross correlation from W to epsilon. This will be exactly the impulse response I want. The noise, of course, will have a more complicated transfer function, but the point to note here is that if I create the new noise V here, which is just this part, it will be uncorrelated with W because I have made the assumption that my X and T and E of T tilde are uncorrelated. That will follow through so that V will be uncorrelated with W still. That means that I have a transfer function with an input W, which is white. V is uncorrelated to W, and that means that I can estimate the impulse response by the cross correlation between epsilon and W, like this. If I then look at the confidence interval for this estimated cross correlation, I see that I can say roughly make it into 1 over n. So I can get a bound which is plus minus 2 over n, meaning that I can estimate the impulse response, say like this, and then I will look at the confidence interval and I will determine which of these are significant components. So in this case it would only be these 3 components here, and from that I will identify the impulse response. So in this case I will have an impulse response looking like this and nothing more, and from that I will determine D, R and S. And D is of course again just the delay between 0 and when the impulse response starts. Okay, so when I have estimated the cross correlation, I can use that to determine D, R, and S. So from those, I will now be able to estimate the B and the A2 polynomials if I treat epsilon as a white process. Of course, this is not correct, but it will give me an initial estimate of B and A2. And the way I will then deal with it is I will create an estimate of my residual. So this is an estimate of the residual by just subtracting out the estimated component. So basically what I'm doing is I'm taking the measured data, y of t, and I'm subtracting out everything that I have perceived that I am able to model using my input. And what I have left, that is my residual, and from that I can then proceed to determine an ARMA model of E tilde, just as we've been done earlier in the course, and from that we can determine the model orders of A1 and C1, that is P and Q, as we have done before. Then what I do is that now I have all the model orders that I'm looking for. I have the P, the Q, the R, the S, and the D, and I can then re-estimate all the polynomials together. Here it is important that I should not be using my earlier estimates because they were just rough estimates without using the structure of E tilde. Basically, we made the assumption that it was white. So those are going to be flawed. So I really need to re-estimate all my coefficients when I have my full model orders. Then after I've done that, I will proceed to examine whether the model is white or not. And if it is white, then of course I have been able to create a model that captured the input successfully. It is also interesting to look at how much the input is then correlated with the residual. So if I would look at the cross correlation between epsilon tilde hat and x of t, this should be low because I should not have any correlation in my residual between the input and the residual, because it should all be taken out by the subtraction of this part. So let's have an example. So this is my input to the process, and this is the output. The first thing I would do is I would follow the procedure I have and create a model for the A3 and the C3 polynomials such that I can write this as a white input process driving the system. So to do that, we will need to look at the Akvinde-Pak. This is the Akvinde-Pak of x of t. And always we will start modeling the AR part of the ARMA. So I will look at the AR part of the process. That is done by looking at the PAKV. And I see that I have quite a strong component here at position 2 and at position 6. There is also a quite strong component at 4, you might notice, but I would rather try to have a simple model. So I'm hoping that the component at 4 might be a result of the coefficient at 2 and 6, and therefore I will initially start by just having the A2 and the A6 model. Obviously, I might be wrong in this assumption, and then I will have to go back and add in the A4 component. But to make the process smooth, I will start with just a few coefficients. If that doesn't work, I will add the 4. If that doesn't work, maybe I need to add the 1, and so forth. But so I will start with the A3 polynomial with just 2 coefficients. So I will estimate these, and I will compute the residual. And then I will look at the residual and try to determine the MA part. So I started with the AR part, now I go to the MA part, and I look at the coefficients in the ACF to determine what should I use as a model for the MA part. And as you can see here, I have a quite strong component at 14 and at 1. There is also other components that are strong. I mean, there is, for noticing this one and this one. Maybe I even need things like this in my model. But again, in the interest of simplicity, I will just use the most dominant component. So I will add the C1 and the C4, and then I will re-estimate the residual using my polynomial. Now, if I do that, in this case, I will get an estimate which is white. So it actually covers the model well, and now I'm able to model the input using just these coefficients. If that was not the case, I would go back and try to add components to the A3 polynomial, re-estimate, then go back and add components to the C3 component, and so forth, until I got something that is deemed white. But in this case, I got it already now, so that means that I have these 2 polynomials that I'm interested in. I will then compute the epsilon and w processes and look at their cross correlation, scaling it like this and plotting the scaled version. So here I look at the cross correlation, and what you can see is that there is a delay. This is 0, so you can see the delay immediately like that. So this suggests that I should pick a delay of 3. Then the first component is a significant component. This is counting 0, 1, 2, 3. So I should have an S to be about 3, and it has this exponentially ringing behavior. So it seems suitable to use a model of R is equal to 2. Clearly, this might be difficult to call. I mean, you could say that this is it's continuing. Maybe these components are significant. Maybe I should use another model. You need to start somewhere. So this is my initial start, and if that doesn't work, I will have to go back and pick another set. There will be often things going on at the negative lags, but remember, we are assuming the process to be causal, so we're not actually interested in those. We assume those to be nothing. There's also strong things happening far away that might be significant, but probably not, since we're making the assumption here that we will have a relatively short impulse response from the input to the output, being the case that a more complicated response is typically too hard for us to handle at this stage. So I will subtract out the things that I can see in my output data that can be described by x of t. So I will compute the part that I can describe by x of t and subtract it from y of t. And then I will look at the ACF and the PACF of the residual. So this is the ACF and the PACF of E tilde of t that we're looking at here. And again, I will start looking at the PACF part to determine the AR components. In this case, it seems like I will have a strong component 1 and 3. And so it seems reasonable that I should start trying with those. I mean, as you can see, that maybe I should have 2 and 4 as well, but I try first with the most dominant component. And if I do that and estimate the coefficients, I will get this polynomial. And then I see that I will have to have a C1 component, so I will re-estimate, and this is what I get when I have a C1 component. And if I do that, I get a residual which is white. So if I take then all these model orders and re-estimate the coefficients, I will get this model. And looking at that, I will get a white residual overall. It is interesting to notice here that the coefficients changed when I re-estimate. This is the first model was simplistic and cannot capture it well enough. So the second thing to notice here is that if I looked at, remember the impulse response, you can see that the coefficients here, in this case it was about minus 0.4, is exactly the value I had here. The second value, 0.9, is essentially that value, and the third value is at 0.48. So from the cross correlation, I could actually see the B components relatively well.